Hi, welcome to MEEN 2021, our Statics and Dynamics class from Texas A&M University. My name is Arun Srinivasa, and today we are going to talk about torque, moment, and how forces are related and how they act and how to compute their quantitatively, how to measure their action. Okay, so let's start. Okay, first up, what are we trying to learn in this section? Okay, item 1, what happens to a rigid body when a single force acts on it? So we're going to say what happens if a force acts, and you're thinking, what the heck? I mean, we know that it's going to move, but you know, in your physics class, people only focused on particles. Now we're going to talk about rigid bodies. You will see that it moves in a slightly different way than you might expect or you might think about right now, but it will become obvious to you when we look at it. Okay, that's item 1. How do we quantify this action? That's item 2. And what's the systematic procedure for computing the actions in a way that is simple and easy to use later? I told you royal root, right? So what we're going to do is we're going to try, there are shortcuts. But we will take the royal root. Why? Because we want to make sure that it works all the time. We will never look at things that work only for special cases. Okay? Very good. Okay, let's start. So what actually does a force do a rigid body? So I'm going to show you a little video to explain what happens. Okay? So what it is that I have a small rigid body here. That's a rigid body, and I'm going to apply a force to it. So before I do that, what do you think will happen? You know, so let's see if, did you just think about it for a second and you will see. I'm going to pull that. When I pull it, you can see what happens, right? So you can see, of course, it's moving and all that. But what I want you to realize is that when a force is applied to a point on a rigid body, it will do two things, not just one thing. It will not only make it slide, it also makes it rotate. The tendency of the force to cause it to rotate is called moment of a force or torque. You could see that when we did this thing, no? So watch, I'll play this again. You will see. First it rotated and then it slid, although the force was the same. Now why it first rotates and slides and all that is, we'll leave it to Newton. But I just want you to understand that the rotation, the tendency of a force to cause rotations is called moment of a force. Okay? Very good. So why is this important? So let's look at a very simple thing, how to fix a car tire.
You won't get too far without that. In fact, you should check your spare tire's pressure regularly just to make sure it's fully inflated. When you got a flat, the last thing you need is a useless spare. Now the first thing to do is park your car on the most level ground you can find, and then engage the parking brake. If you've got a manual transmission, make it first gear or reverse. For automatics, you'll want it in park. Next, take off the hubcap if your car has one. Use your wrench to partially loosen the lug nuts. You're not sure.
Now notice, I paused it here because I want you to notice here's the lug wrench. I mean, here's the lug nut, here's the lug wrench. Notice two things. One, she's holding it as far away from the lug nut as she could, and she's applying a force that's perpendicular to the wrench, right? So those are two key things. Another thing that you notice very interesting is that she didn't talk about jacking up the car yet. She's doing it before she jacks up the car. I wanted to, some of you may already know why, but this is a very key thing. So I want you to notice that she will talk about jacking up the car only afterwards. Okay. Notice she's applying a single force with both her hands along that.
How to remove the hubcap? Just check your owner's manual. Also, check to see if your car has plastic covers over the lug nuts like this one does. If so, then take them off first. Your lug nut wrench probably won't fit over them. Make sure you put them somewhere safe so you don't lose any of them. Now to take the lug nuts off, go in a star pattern, loosening one of the lug nuts a half turn, and then loosening the one opposite to it. Work your way across the tire until all the lug nuts are unscrewed at half turn. Before you jack up the car, put a heavy object, like a brick, in front of the wheel diagonally opposite the flat tire to prevent the car from slipping. Here's where the jack comes in. Put it under the car's frame near the wheel.
Notice the lug nuts are loose before she puts up the jack, okay?
Flat. There's a thin lip that runs along the side of your car. That's usually where the jack goes. Your car might be different though, so
Now, the next thing I want you to notice is that this is a different way of turning. Can you see that she has now two forces separated by a distance, and she is actually pushing on one and pulling on the other. This kind of a way of generating a torque or a moment is called a couple force or a couple moment. Okay, so there are two ways. You remember in the earlier stage, she just pushed it with one hand, and that's one way. And in this phase, she is pushing it with two hands, and that's a different way. Okay, two hands like a bicycle, and that's a different way. So a bicycle is a very good example of a couple moment. Okay, so we'll talk about that also a little bit. So that's what you do. And then afterwards, if you want to know more about it, you can always learn about it later. So the main point which I want to talk to you about is that the rotational action around a pivot depends not only upon how much force you are applying, but on the perpendicular distance from the pivot. So let us see what I mean. Here is the pivot. Here is where I am applying the force. Can you see that line? That's where I am applying the force. Okay. So here is where I am applying the force. Now let's see what happens if I apply the force. Let's say I get that much moment. That red bar tells you how much moment I get. If I apply the force a little bit closer, I will get a little bit less moment. If I get closer, less. If I apply the force directly at the pivot, there is no torque. It's not going to turn this thing. So just to make sure you understand, there, can you see that? 2, 3, 1, 2, 3. Can you see how it decreases? So it does matter how far the force is away from the pivot. Okay. Now that's one item. The second thing is, we are back to the same situation. I have a force and the setup there. Now what happens is, I'm not going to change where the force is acting, but I'm going to change the angle of the force. So I'm going to say, okay, there. You can see that the torque got less. It got even less. If it is parallel, I get 0. So just to make sure, there, see. Now, how do I quantify these two things? Everything depends upon what is called perpendicular distance. That is this distance. Okay. Now you can see it's a fairly large perpendicular distance. If the angle changes, you can see that this distance is now slightly smaller, and you can see now the distance is small. And when it's completely parallel, the distance is 0. Notice even here it was the same thing. So the most important idea is that not only the force, but what is its perpendicular distance from the pivot. Now it turns out to be somewhat hard. It is not the direct distance. This distance does not really matter. It's actually this distance that matters, the perpendicular distance. That distance that matters, not that. So we need to have a way of systematically identifying this perpendicular distance, and we have two ways of doing this. One is the trigonometric way, and the other one is by using vector algebra. You need to know both, because the trigonometric way gives you a graphical pictorial way, and of course vector algebra gives you the vectorial way. Again, you know, notice this thing from picture to vector. That's what we're talking about. Okay, so let's do that. So the main thing is to remember is that the moment magnitude equals gap distance times force magnitude. I will talk to you about that in a second. So here is the object on which there is a force F is acting somewhere, and I am very much interested in finding out what is the torque, what is the moment of F around the pivot. That's what I'm interested in. So how would I do this? I'm going to do this by drawing or trigonometry. You will see that. So first step is draw a line through the force. There, I have drawn it. Okay. Second step, draw a parallel line through the pivot. There. That's the parallel line through the pivot. And then use trigonometry to find the gap distance. That's the gap distance. That's how far away the parallel line and the original force were. Now it's very easy. You just have to do gap distance times force magnitude. And the sign of it comes from what is called the right hand rule. You put your palm at the pivot. Can you see that's the pivot? there's your palm. The thumb points in the direction of where the force acts, that direction. Your fingers point in the direction of the force. Then in order to do that, if your palm is facing your page, then the moment is positive. If the back of your hand has to face it, then the moment is negative. This is how trigonometry works. Okay. The advantage is you can clearly see where the gap distance is and things like that. The use of this is for doing qualitative evaluations. You can quickly figure out whether the force, so if you look at this one, you can see that the palm is up, the palm is like that, it's up. So what happens is you are going to get a counterclockwise torque. It's going to rotate that way, right? So the body is likely to rotate that way. So this means positive means counterclockwise rotation, negative means clockwise rotation. So what do? Put your palm at the pivot, point with your thumb pointing towards the location of the force and your fingers pointing towards the direction of the force. And then whichever way you have to put it will tell you whether it's going clockwise or counterclockwise. So if the palm is facing your face, then it's clockwise, counterclockwise. If the back of your hand is facing your face, then it's clockwise. Okay. So figure it out. This is how it works. Excellent. Now let's look at the next one. The next one is we want to do a quantitative evaluation which works all the time. So now what we do is we calculate the moment vector, and what, just like and I'm sure in your earlier classes they have told you R cross F, and you know royal root says don't memorize symbolic versions, memorize what is written there. Line vector from pivot to force cross force vector will give you moment vector. What does it say? Line vector from pivot to force cross force vector. This is what you should memorize. Don't remember R cross F. Okay, memorization, this works better. So how does that work? Here's the force, same problem. Here's the pivot. First step, put axis at the pivot, X and Y, and be smart about orienting it. See, find the best way so that it's easy for you to do the calculations. You'll have to think about that a little bit. Okay. Of course, if you're stupid about it, it just means you'll have to do a little bit longer. Nothing will happen if you choose a strange axis. It may get a little bit more complicated, but it will always work. Okay, so that's item 1. The second thing is find the line vector from the pivot to any point on the force. It doesn't have to be here. If it's easier to find the line vector to this point, doesn't matter. You may want to find that. It really doesn't, as long as it's on the line of this force. So for all you know, if this point is easy to find, you can find this line vector. So this will be x bar comma 0, whatever I mean. You see what I mean? This will be x hat comma y hat. This is x comma y. Pick something along the line. Very good. Then find the force vector, which is f of x. F is fx fy. So now you have R is xy, f is fx xy. All you have to do is do cross product. M equals R cross f. But in 2D, it's even easier. All you have to do is this. xfy minus yfx. That's all. That's actually R cross f in 2D. xfy minus yfx, and the direction will be z, that is pointing out of the page. And if you get this number to be positive, then it says counterclockwise rotation. If it is negative, it is clockwise rotation. That's all. xfy minus yfx. And the beauty of this is you can easily do this even in 3D. There's nothing to it. That's what we're going to do. Next one, if you have a force and it has it's as usual, I have one point R for which I know x, y, z, then the moment along the x-axis is yfz minus zfy. So if you remember just this part, mx equal to yfz, the other one will be zy. Notice this side there's no x, this side there's no y, this side there's no z. So what does mx mean? It means how fast am I turning around the x-axis? That is mx. What does my mean? How fast am I turning around the y-axis? That is my. mz means how fast am I turning around the z-axis? That's mz. Okay. And so if I remember if I know how to write mx equal to yfz, the next one is easy. So you can see x, y, z. The next one is z, f, y. Then what do I do for my? I go to my little circle here, and this circle is very, very useful, because even if you are doing cross product, you can see I cross j equal to k, k cross I equal to j. If I go backwards, it's negative. So this way positive, this way negative. So it's pretty easy. Fy, so y is going to z, so that will become z. Z is going to x, that will become x, and the other one is x, fz. And mz will be, okay, z is going to x, x goes to y, and then y, fx. This was the formula that we needed for 2D. You can see how the 3D and 2D formulae are actually connected. The main point is, this is exactly what you will get by doing R cross F. This is just a convenient way of doing it, and there's an even more convenient way of doing it, which we will use pretty heavily, which is do this in a tabular form. This is the absolute super highway. What you do is, for each point where there is a force, P1, P2, P3, P4, you write down where the point is, what force is acting there, what is the moment, and once you fill this table out, there is nothing to doing the equations of equilibrium. All you have to do is, if you add up all of this, you will get sum of all the forces in the x direction. If you add up all of this, you'll get sum of all the forces in the y. If you add up all of this, you'll get sum of all forces in the z. Same thing with mx, same thing with my, same thing with mz. So it's a tabular column. It's easy to remember. You don't have to do it. This thing is R, this thing is F, and this thing is R cross F. And if your calculator, or if you are more comfortable doing that, that's also fine, as long as you list R, F and R cross F. That's all we are doing. Okay, thank you very much.